We just talked about the definitions of relations and functions, and then how we can look at a relation that's represented in various different forms: table, mapping, graph, equation. Could be written as a set, and how we extract the domain and the range from that, and how we determine if it's a function or not. And that's really all you're doing today. That's it. So remember, relation is just any logical connection between input values, which are the x values, the set of all those we call the domain, and the output values, which are the y values, and the set of all the output values, remember, we call the range. It's discrete if it's got a finite number of ordered pairs. It's continuous if it's a graph that has an infinite number of points on the graph. Okay. Remember, a function, we had kind of an easy, informal definition that worked pretty well for a function. We said that it's a function, the rule for a function is, you fill this in, for each input, there's exactly what?
One out.
For each input, there's exactly one output. Yeah. And if that's true, then it's a function. So we have an example. Thursday we said that this is an example of a set of ordered pairs that is a function because each of the three inputs only has one output. However, this was an example of a relation that's not a function because the input 1 was output to two different values. So it failed the test, not a function. Vertical line test, remember, if we sweep a vertical line across a graph and it never intersects the graph in more than one place at a time, then it's a function. So this blue graph would pass, the red graph would fail. Right? We looked at some examples just real quickly. You'll see examples of each of these on the assignment. If I give you a set using set notation, a set of ordered pairs, remember that the domain is just going to be all of the x values. When we write a set out of discrete values, we always want to put the numbers in increasing order, numerical order. Same for the range. Okay, we don't repeat, if there are repeated x or y values, we don't write them multiple times in the domain or the range, just write them once. Tables, same kind of thing, right? Tables, we've just got the domain would just be all of the x values, we put them in order for the domain. The range is all the y values, put them in order for the range. Okay? So these are all functions because each x value has one output. But remember, we looked at a couple examples like this guy. There's a mapping. This was not a function because we had a single x value that output to two y values, right? Single input was mapped to two outputs, so that makes it not a function. This one was okay though, right? We started, we looked at some graphs of discrete values, and all you have to do here to get the domain and the range is just list the x coordinates of all the points in increasing order. For the range, we just list the y coordinates from bottom up in increasing order. This one was clearly not a function because we had 2 points that lined up vertically, so it failed that vertical line test. And then here's kind of the last part. We looked at some examples then of continuous functions that weren't discrete. Here's right. Most of the assignment is going to be about this stuff. So let's just take a second and remember how this works. So if I've got this continuous function with an infinite number of points, when I write the domain and the range, I can't write it using sets anymore because there are an infinite number of points. I have to write it as something like an inequality or using interval notation. So we just want to find all of the x values that are graphed in this function. That's the domain. And then all of the y values, all the y coordinates that are graphed in the points in that graph would be the range. So an easy trick, and this is kind of one of the things that we introduced on Thursday, is to do what we call that projection, right? Where we're going to project all of the points in the graph, we're going to project them vertically onto the x-axis. And when we project them onto the x-axis, that gives us a specific graph of the domain, right? So for example, here's the leftmost point on the graph. That one's, if we project it onto the x-axis, it just moves vertically up to that point right there, right? This guy just moves vertically up to that point. There's an infinite number of points. In this case, we had the graph that we had a left endpoint at -4, and then it went on forever to the right. Agreed? So we got the domain x is greater than or equal to -4. How do we write that? Just quick review, because you're going to be asked to do this on the assignment. How would I write that using interval notation? So here's my interval, right? Every time I graph an interval, and I think it's very helpful to actually graph the domain or the range, on a number line, or just on the x-axis, for example, to be able to see the intervals that you have to represent. Every time I have to pick my pen up and put it down, even if I leave it down forever, every time I put my pen down, I'm drawing an interval. So there were some instances like last unit where we ended up having multiple intervals. I might have an interval over here somewhere, I pick my pen up, and then there's an interval over there, right? Every time I put my pen down to make an infinite line or a line segment or array, that's an interval. Well, there's only one interval here. It starts at -4 and goes to the right forever. When we write interval notation, for each interval, we always have to do a comma in an ordered pair, right? To the left of the comma goes the left endpoint of the interval, and to the right of the comma goes the right endpoint. So what is the left endpoint of this interval that represents the domain?
Bracket.
Oh, I'm going to have to have a bracket, and then what? -4. Good. Okay, it's a bracket because it includes -4 in the inequality, and it's shaded in with a solid dot. What's the right endpoint of that interval? Infinity. Yeah, it just goes to the right forever, and so then I need parentheses there, don't I? Right. So that would be the domain of that function. Now, what about the range? What do we say about the range of this one? Is there an upper or a lower limit to the y values on this one? No, if I zoom out forever, the y values are going to go up forever and down forever, aren't they? Right. So if I do a projection, thank you. If I do a projection onto the y-axis, it's going to cover the whole y-axis, and so it's just all real numbers, right? So we just put our R in there for all real numbers. It's not the fancy R from the menu, it's just a capital R off the keyboard, that's all it is. Is it a function? No, it wasn't, because there are places where it lines up vertically, right? Where a vertical line intersects the function or intersects the graph in more than one place, so it fails that test. What about over here? Same kind of thing we said. If we project all of these points in this ellipse onto the x-axis, well, I'd end up with my leftmost point at -2 and my rightmost point at +5, right? And so the domain would just look like a line segment with solid endpoints at the left and the right. And the way we would say that would just be x is greater than or equal to -2 and less than or equal to 5, right? How would I write that using interval notation? Okay, I gotta have a bracket because it's a solid endpoint. I'm including the equal sign. Left endpoint is -2. What's my right endpoint? I need another bracket, don't I? Now what about the range? Same thing. If I'm just going to project all of these points onto the y-axis horizontally, if I squeeze all these points onto the y-axis, I've got my lower limit. In this case, instead of a left endpoint, we're talking vertical stuff, right? It's the y-axis. So the left is equivalent to the bottom, isn't it? Right? If we're going from -infinity up to +infinity, just like we do on the x-axis, well, the positive direction is up. So the lower limit's the bottom value, the upper limit's the top value. So we'd say y is greater than or equal to, looks like -2, and less than or equal to +4. And so, of course, that would just give us, using interval notation, I've got brackets, and then -2 is my left endpoint, or my lower endpoint. +4 is my upper endpoint. Okay. And then the last one we had, we looked at an example with where we had to use Desmos to graph something. And we'll look at a couple of quick examples here. So these are the kinds of things, these are just taken from the e-ticket in the homework. So what would I enter for my domain on this one? It wants the domain. I'll write it up here. I gotta have, now this is discrete, so I use a set. 1. What's next? The domain. 3, good. Everybody, what's next? 7. Do I write 7 twice? No, I do not. Good. How about the range? Good. Okay. Is it a function? Yes or no? No, it is not. Good. And the reason it's not, we can see that pretty clearly here. It's not a function because there and there, right? Look, I've got the input value 7, single input value, outputs to two y values, two output values. So it fails the function test, doesn't it? Each input does not have a single output. The input 7 has two outputs. It's not a function. Here's an example of a continuous one. Real quick, if I were to project well, what's the domain of this one? What's the domain? All reals, good, because if I zoomed out far enough, this function would go to the left forever and the right forever, wouldn't it? Okay, we're looking at just a finite window here. We can't see the whole thing, right? We have to always choose. We can't see infinitely far, but the domain is all reals. Now, what about the range? Okay, y is less than or equal to 4. Very good. Y is less than or equal to 4. They want this using inequality, so we just leave it like that. Now remember, the way we can see that is if I were to project all of these points onto the y-axis, I would have a top value at 4, and then it would just go down forever, wouldn't it? Okay, good. How about this one? Maybe slightly trickier. If I'm looking at the domain, if I project this onto the x-axis, what can you tell me about the endpoints I'm going to get? Rodney, where's the left endpoint going to be if I project this onto the x-axis? 2. 2. Good, so we're going to project this point up there vertically. Open or closed? Open, because that's not included in the function, right? You ask yourself, if you want to know, is it open or closed? You ask yourself, is that an x value that's a part of the function, right? Could an ant walking on this function stand at that point? No, he can't. He couldn't stand on that point because it's not there, right? There is no endpoint. So we get an open endpoint there. Where's the other endpoint? At 4, and that one's closed, isn't it? And so there's my domain. Now, how would I say that using interval notation?
2, 4, and
Good.
parentheses in a bracket.
Good. Left endpoint 2, right endpoint 4. What's on the left, did you say?
Parentheses.
Parentheses.
Bracket.
Bracket. Good.
Yeah.
Everybody see that? Okay. How about the range? If I project this thing horizontally onto the y-axis, why don't you click those closed all the way, please? If I project this horizontally onto the y-axis, what's going to be my top value? Say it again. Negative. We're closely.
Oh, is that 5?
Yeah. Negative 5. So negative 5. Now here's my question on this one. You tell me, is that going to be open or closed? Closed, isn't it? Right? It's closed because there is a point on the function. It's right there where an ant could have a y value of negative 3, right? Okay, what about the other? What's the bottom end point going to be? Negative 6. And that comes from both of those, doesn't it? Open or closed?
Closed.
Closed, good. Because even though the left endpoint of that graph is open, the right one is closed. And you ask yourself the question, could an ant stand on a y value of negative 6? Yeah, he could. Right there, right? Or she could, either way. I don't know what they are. So there's my range. So how would I say that using interval notation? Now, it's easy to do, but it's vertical, so you got to think about it just a little bit. What's the range going to be? Instead of left, what does it become? The lower end point. Now, instead of being the left point, like the one on the x-axis, is well, it's going vertically, though. So the lower end point would be the bottom or the top? The bottom. Okay, so what's the bottom going to be? Brackets. And what is the value? Negative 6. The right end point, or not the right, the top, I guess would be, correct? Negative 5. And you know you did it right if the numbers are increasing from left to right. See what I'm saying? If you want to think about it this way, I don't think you need to. I think it's almost more hassle than it's worth. But if you want to think of it in terms of left and right, it'd be like taking the y-axis and just doing that with it, right? Just rotating it 90 degrees clockwise. So the positive direction, instead of being up, it's to the right. But you don't probably have to do that. Just think of it in terms of lower and upper, right? Is it a function? Yeah, it is. If I slide a vertical line across, it passes the test, doesn't it? So yes, it is. Okay, real quick, what about one like this, where we're given a function and we have to graph it because they don't give us the graph. Well, that's where we use the Desmos utility, right? So all we have to do with the Desmos utility makes it real simple. We just type in the equation. We don't have to solve for y like you do with the TI-84. You just type it in and it graphs it for you. Okay, now if I click on the graph, notice it shows up, it gives me a point that I can click on over here that's the vertex. That's important because that's the rightmost point. Everybody see that? So what's the range of this function? You can, you bet. What's the range of this function? Or of this relation? I guess I shouldn't say function maybe. All reals. If I zoom out far enough, does everybody agree that this function or this graph is going to go up forever and down forever if I zoom out far enough? Yeah. So we know the range is all reals. What about the domain? If I project the domain onto the x-axis, which I guess is, where is that? Up here somewhere, right? What would happen? What's going to be the rightmost value? X equals what? 9. Good. That's the x-coordinate, isn't it? Right? So this point is going to project up onto the x-axis at a value of positive 9, and then everything to the left would be filled in. Everybody agree? Okay? So there it is, right? If we want to write using inequality notation, you already told me that the range is all reals. What about the domain? Well, that's going to be y is what?
Less than 9.
Less than or equal to. And we know it's equal to because an ant could stand there, right? So y is less than or equal to 9, and that's where that 9 is coming from. Okay, is it a function? No, it fails the vertical line test. Okay, last one. This is kind of a good one to end on. This is interesting. Did I tell you about this earlier? I don't think I did. Okay, so write the domain and range of the relation to determine if the graph represents a function. It says the red line is an asymptote. Okay, well, asymptote is a really important word in math. An asymptote is something that guides the behavior of the function, way out, either at positive infinity as we approach positive infinity horizontally or negative infinity horizontally. This is something we were just talking about in calculus a bunch here at the beginning of the year. There's a concept called a limit that's related to the stuff that we're talking about in this example. We won't get to that till later in the year, but we'll just brush that topic later in the year. But in calculus, you spend a lot of time with it. So here's what it does. What the asymptote does is it's kind of the ceiling that you're approaching on this function. Now the function could have been approaching it from the top, and then it would have been like the floor that it's approaching, right? As an ant walks to the left along this function, it's no mystery what happens. The ant's going to go down forever and to the left forever, right? But as the ant goes to the right, look what happens. As the ant moves to the right forever, so the x value is getting infinitely large, what's the y value doing, do you think? It's growing, but ever more slowly, right? What value is it always trying to get to? 5. But it never gets there. That's what an asymptote does. Here's a good example to explain this, and you hold on to your head because you don't want them to explode or anything. This is kind of a big thought here, but it's interesting. So let's say for the rest of eternity, every second for the rest of eternity, forever and ever, I'm just going to cut my distance to the door in half. So here's 1 second, 2 seconds, 3 seconds, 4 seconds, etc. Do I ever get to the door?
No.
I never get to the door. That's a crazy thing, though. Think about that. If I'm always moving towards the door, because I never stop moving, do I? I just move ever more slowly all the time. Now, here's another question, follow-up question. If I had an infinitely fine Sharpie, here are the rules. I can't mark on the door, but I can mark wherever I want to on the floor, as long as it's not actually on the door. So I could put a mark here, or I could put it closer, or I could put it even closer. It's infinitely fine. And let's assume that we have some kind of a mechanical arm that we can use to make points as close as we want to the door, but they can never be on the door. is there any point I could ever make on the floor that I won't eventually step on?
No.
It's a profound question. You're right, there isn't. There's no point I could make on the floor that I won't eventually step on, right? And yet, do I ever get to the door? Not weird, right? It's a weird concept.
You know what's crazy?
What's that?
You know the universe is growing, right? Like
Mhm.
ever so slowly every second, whatever.
Mhm.
What is it growing into? Like, you know what I'm
That's a
saying?
great question, and I really want to talk about that one, so hold that thought. But that's a really good question. That's very interesting stuff. We will, I promise you, we'll have some days where we can kind of drift into some
Speaking
conversations.
of drift, ocean pressure.
We'll get to that too. We'll get to that too. So let's look at this. Let's look at this example. Well, you already told me that the domain is all real numbers, right? That's no big deal. But what about the range? If I project this blue function onto the y-axis to look at the range, what am I going to get? Is there going to be an endpoint? Right? If I take all these points, like each one of these points, all I'm going to do is, like this guy right here is just going to go over to the right and end up right there. This point right here is going to go over to the left and end up right there. Is there going to be an endpoint on the y-axis to my range? There is. You're right. There's going to be an endpoint. Well, what is it? 5. Okay. Open or closed?
Open.
Open, because it's an asymptote. You can never get there, right? So I get an open endpoint there. So we can get this, we say in math, we can get arbitrarily close to 5, as close as you can imagine, but we never actually get there. And then it just goes down forever, doesn't it? Right? So what would, if I'm writing the domain in the range here, what is my range then? Just write it as an inequality. Y is less than 5. Exactly. Everybody see that? Okay, I'm going to turn you loose. So you got a 6-question e-ticket that I want done before the end of the period. You can do it. It's very short. And then after that, you can move on to the assignment, which is also pretty short. But you may not get that finished. You might, but you might not.